Welcome to Chem We Talk, a channel where we're not afraid to talk about any chemistry topic. In today's video, we'll focus on the concept of chemical equilibrium. More specifically, we're going to emphasize how to manipulate the equilibrium constant Kc. Okay, as usual, before we get started, let's just look at the questions that we're going to answer in today's video, starting by what is the definition of chemical equilibrium, what is the equilibrium constant Kc, and what happens to Kc when three things happen. First one is when the coefficients of a reaction are multiplied by a factor. Secondly, when the reaction is reversed. And three, when two or more reactions are added together. And more importantly, the main goal of this video is explaining why those things happen instead of just memorizing it. Okay, so let's just start by looking at this reaction where we have A plus B yielding C and D. And differently than previous chapters where I used to see a single arrow, now we see this double arrow, which is going to mean that the reaction is at an equilibrium. But what does equilibrium mean in chemistry? Okay, instead of having, as I said, the single arrow going one way, that means that A and B are now being consumed to produce C and D, but some of C and D can also react together back to produce A and B. So the reaction is going in both towards the right direction and towards the left direction. But the actual definition is when the rate of the forward reaction equals to the rate of the reverse reaction. And let's go back to our rate law chapter or kinetics chapter and express the rate law of the forward and reverse reaction, set them equal to each other. Remember correctly, let's just label Kf as K of the forward reaction. It's going to be equal to the concentration of A raised to the coefficient in front of it, A, and B raised to the coefficient, which is going to be this little b, equals to the K of the reverse reaction, times the concentration of C and concentration of D raised to their respective exponents. And remember, we can only raise to the coefficients or the stoichiometry coefficients because in equilibrium we have elementary reactions, which are reactions that occur in a single step. If that were not the case, we would need to have those reaction tables. All right, let's just rearrange this equation a little bit more. Let's just combine in one side the K's and the other side the concentrations. And if we divide both sides by Kr, this Kr is going to cancel and going to end up on the left side. And then we divide this side here by concentration of A, concentration of B. We can rearrange this equation into concentration of C to the C, concentration of D to the D, divided by the concentration of the A and concentration of B to the B. This division here between the K of the forward and K of the reverse, that's going to be called the Kc or the equilibrium constant. But more importantly, something that we need to memorize here is that for Kc, we're going to have products divided by reactants, and most importantly, raised to their exponents. Okay, so we have C to the C, D to the D, A to the A, and B to the B. And just one thing that's highly important as well to memorize is that no solids or pure liquids are included. So let's say if this here was, instead of being aqueous, was a liquid, it would not be included in your equilibrium constant expression. Okay, and we're going to discuss more in depth in a different video why that's the case. All right, so let's just do some practice problems and just write down the equilibrium constant for this reaction. Okay, so first thing we need to notice, all of those species are aqueous, so we're good. So everything is going to show up in our expression, and we're going to do products over reactants raised to the coefficient. So our product C, so it's going to be C cubed because of the coefficient, divided by A, coefficient is 1, and B squared because the coefficient is 2. Okay, let's look at a different problem, very similar. Still, we're looking for what is the equilibrium constant. The reaction looks pretty similar, still only aqueous species. And C is product, B and A are reactants, so we just write, again, products over reactants raised to their respective exponent. So now it's going to be C to the 6, A squared times B to the 4th because of the coefficients. Okay, let's just draw some conclusions. When we look at the first example and the second example, what happens to the coefficients? We can see that from here to here, the coefficients double, right? So it used to be 1a, now it's 2a, 2b, now it's 4b, 3c, now we are 6c. And let's just rewrite here the equilibrium constants for them. So for this one was c cubed, a and b squared. This one, c to the 6, a squared, and b to the 4th. And let's just try to draw some conclusions here. We can note that the second reaction, which is c to the 6a squared b4, is the same thing as multiplying the k twice. So you can see here that c cubed ab squared, c cubed ab squared. So it's the same thing as squaring the first k. So the take-home message that we want to take from here is that when multiplying a reaction by a coefficient, like here we did by 2, the new k, or the k for the new expression, is going to be equals to the original k raised to that factor. So from here to here, multiply by 2. So we just raise that k to the second power. Okay, let's look at this example here. All right, so we have this first reaction with a given k arbitrarily called k1. And let's try to calculate the k for the second reaction. Let's see what happened. Let's compare those two reactions. And I think it's easy to note that from here to here, all the coefficients triple, right? So A is now 3A, 2B is now 6B, 3C now 9C. So if we multiply by 3, that's going to be applied to the exponent of your k. So it used to be k1, now the 3 that we multiplied becomes the exponent, so this new k for this reaction is k to the third. Okay, so let's look at the first and third reaction and see what happened. This one's not as obvious, but from here to here, 0.25, 2b to 0.5, and 3c to 0.75. And it turns out that from here to here, we are multiplying by 0.25, which is the same thing as multiply by 1/4. And we're going to do exactly the same thing. So if this here was k1, and we multiply it by this factor, those factors will become the exponent. So the new k would be k1 raised to 0.25 or k1 raised to 1/4, which is the same thing. And if you remember your algebra correctly, that also corresponds to the fourth root. Okay, so whatever you do to the coefficients, you do to the exponent of your case. All right, moving to a different scenario. Now we were given two reactions with non-k values, and the question is asking for a third k value for a third different reaction. And let's look at those reactions first. We have A and B and C, and then C, D, and E. And in our product, or in our final reaction, we have only A, B, D, and E. So C disappears. So it looks like there's some way we need to cancel out the C's, and that's going to be through addition of reactions. But let's look at what happens. So the K for the first reaction is simply going to be C raised to 3, right? Products or reactants raised to the coefficients, A and B squared. The K for the second one will be E squared, because of the product E and the coefficient 2, C cubed and D to the fourth. And what is the K for the third reaction? Now we have only E as our product, and we have A, B, and D as reactants. Okay. Oh, I forgot to put the aqueous symbol there, but this here should be aqueous. Okay, so that's why we're including in the K expression. So that would be E squared, A, B squared, divided by D to the fourth. But let's see if we can draw some relationship between those K's. So what I'm writing here is, this here is the K for the first reaction, so K1. This here is the K for the second reaction. And this here is going to be equals to the K of the third reaction. And we can note that when we multiply those, the C cubed cancels, and we end up with the K3. So basically, if we are adding two reactions, we just multiply the K values. Okay. All right, so let's look at this other problem where you're given this this known reaction with an unknown K by knowing a different K. Okay, so what is the K for this? KIFR just means forward reaction, and SR just means the second reaction, or the first reaction, the second reaction. Okay, so for the K for the first reaction equals to A raised to 1, B raised to 2, divided by C raised to 3. Our K for the second reaction is just going to be C cubed, A and B squared. Okay, and let's just rewrite those over here. And what we can notice is they are sort of reversed, right? So the first reaction equals, in fact, to the reciprocal of the second reaction. So it turns out that once you flip a reaction, so here used to be, the C used to be a reactant, now it is a product. If you flip a reaction, what you're doing is you're just doing products of reactants, but with your products and reactants being swapped. So you just get the reciprocal. So you just do the inverse of that number. So if this K was 2, the K for the reaction that has reverse products and reactants is just going to be 1 over that number. So you get 1/2 for this case. Okay. So as again, just recap, when a reaction is flipped, the new K is just a reciprocal or raised to 2 of the original reaction. Okay, let's just look at this final example here, which is probably the hardest problem in this subject that can happen. Okay, so you're given this unknown reaction again with an unknown K value, and you're given two reactions with known K values. So first thing you need to notice, if you're given two reactions to figure out an unknown K value for another reaction, you're going to need to add those at some point. But it's not going to be as trivial. My recommendation for those problems is let's look at the goal, the ideal reaction, and see where are my reactants and products. So in this case, we have A and B as reactants, so on the left side of the arrow, and we have D on the product. Let's ignore the coefficients for now. Let's look at the first reaction. We have 2A producing E. So your A is on the left side, which matches the side where it should be in the final reaction that we want to look for. Okay, so that's good. The E is on the right, and there's no E on your final reaction, which should be an indication that somehow this E should cancel out at some point. But okay, let's just move to the next reaction. Now we have D on the left side on this reaction, but on the ideal reaction, it is on the right side. And then B is on the right side on this reaction, but in your ideal reaction, it is on the left side. So one thing we should conclude from this is that we need to flip this reaction to make the reactants and products on the right side. And remember, if I flip the reaction, what happens to your K is just going to be the reciprocal. So if it used to be 64, now it is 1 over 64. All right. Now everything is on the right side where they should be, but the coefficients are off. So let's continue analyzing this reaction here. So now we have 9B on the left, while here we only have 3B. So to go from 9B to 3B, we need to divide by 3 or multiply this reaction by 1/3. And if we multiply a reaction by 1/3, we're going to do the same thing to the coefficient. Okay, so it used to be 1 over 64, now it's 1 over 64 raised to 1/3, which is the same thing as a cube root. And if you plug in your calculator, you're going to get equals to 1/4. Okay, so I think we are done with this reaction, because now we have B with the right coefficient on the left, D with the right coefficient on the right, and we still have this 0.5e that's bothering us, but let's just hold on for a second and go back to the first equation. Okay, so we have 2a on the left in this equation, and on the ideal equation we have only 1. So we need to multiply everything by 1/2. And if we multiply by 1/2, what happens to our k? We're going to apply whatever factor we did to the coefficient. It's going to go to the exponent, so it's going to be 9 raised to 1/2, which equals to 3. Okay. Now let's look at those reactions that we manipulated so far. Okay, and we have 3b plus 0.5e, and you see those are reactants on this reaction yielding D, 2D, and then we have A producing 0.5e on this reaction, and now we can see that the 0.5 is on the left side of this reaction and on the right side of this reaction, so they can cancel out, and we end up adding those two reactions together, and we get the ideal equation A plus 3b yielding 2D. And if you're adding reactions, remember, we just multiply the k's, so we solve it for k equals 3 to the 4th. All right, glad you made this far, and let's just do some recap. So chemical equilibrium is reached when the rate of the forward reaction is equal to the rate of the reverse reaction. The Kc is simply going to be products of reactants raised to coefficients, because all those reactions in equilibrium are elementary, which means they happen in a single step, so the coefficients are going to match the exponents are going to match the stoichiometric coefficient. Just be mindful that no solids or liquids are included in the K expression. And then remember that when multiplying the reaction coefficient by a factor, the K will just correspond to the original K raised to that factor. So if you multiply by 2, it's going to be raised by 2. If you multiply by 4, it's going to be raised by 4. If you multiply by 1/3, it's going to be raised to 1/3. Okay, so when we add reactions, the K's get multiplied. And when a reaction is flipped, the Kc is just going to be the reciprocal of the original reaction. All right, thank you again for watching. If you think this video was helpful, please make sure you share that with your friends, colleagues, and lab mates. Follow us on social media, and make sure you check the other videos on the channel. All right, thank you.